Hello, friends, comrades, fellow creatures of life. Why don't you gentlemen or ladies have a Pepsi? Well, it's actually it's a mislabeled container. This is actually Dr. Pepper, not Pepsi. But anyways, now we're going to go over our third lecture in our science series. We covered logical positivism. Now we're going to go over to the solution of the eradication of logical positivism in some sense or another. And we're going to go to logical empiricism, which was made popular in the 1960s. It's more than patterns of experience when speaking of the atomic structure of matter. These are things that are really real. Of course, the problem here is that logical empiricists rejected that nature had depths. They only accepted that nature had surface. In other words, what that means is that logical empiricism still claimed that, one, there are no hidden depths in nature or hidden structures of the world. There's only experience and the world in which it appears to us to be. In short, logical positivism and or empiricism have their valuable ideas preserved by pointing to the limitations of empiricism and a caution to not be overconfident in one's own view, because, matter of fact, we might actually end up being wrong. So let us embrace the teachings of Socrates and by always asking questions in order to get ourselves thinking, and others too. The problems of induction and confirmation. First, we asked, how do observations confirm a scientific theory? Then we ask, what makes an observation count as evidence? The content of claims need to be analyzed because simple confirmation of a hypothesis cannot, in all cases, be just a function of the synthetic logical structure of science itself. Maybe laws should be studied. What makes a law a law? And how do we determine what laws of nature are? What distinguishes law, the hypothesis, from accidental hypotheses? That this is very difficult to determine. David Hume thought wrongly, but at least some of his thoughts had importance in their own right. One of his thoughts was that we can only know what we can see or what we have observed. Hence, since we cannot technically observe the laws of nature in and of themselves, how does science establish a law of nature? David Hume here presents the problem of induction. We infer laws, we do not directly observe them. We can infer that patterns in nature are actually laws. If they are, how do we know? And how do we know that we can know? What happens when there is a break in the patterns or the laws of nature inferred from the patterns? After all, did not David Hume tell us, quote, that the future is not under obligation to mimic the past, end quote? A new discovery might just obliterate physics, the present physics of our very universe. All right. Nelson Goodman's new riddle of induction. Okay, so he addresses the problem that Hume presents. Nelson Goodman was an American philosopher, and he wanted to show that since David Hume, a logic of confirmation or a formal theory of confirmation was in fact possible. He was not showing that confirmation is impossible. He rather argued that one must understand the substance or content of the science in order to confirm, not just the formal logic of the science. And so both form and content or substance must be therefore understood. He gives an example that of an emerald, a very precious gem, of which my tie is green. It's kind of hard to see because it's dark out here, but my tie is green, and emeralds are also green. So he said that an observation that all emeralds are green. Okay, and we conclude that that is a fact of nature. Nelson Goodman proposes that emeralds are also grue. Now you may think, what the hell does that mean? Well, grue is if It is green if first observed before a point in time, and blue if first observed after a point in time. So what Goodman is saying is basically imagine finding 500 emeralds at the present date, okay, all green in color. But afterwards, a blue emerald is found, and all subsequent emeralds are blue. In other words, all emeralds are blue and all emeralds are green are both supported by the same evidence. Thus, multiple competing hypotheses can both be plausible but yield opposite predictions. Hume thought that inductions could not be at all supported by rational logic. Goodman, however, thought that rational logic has the power to support too many inductions. So, what to do when there is not a best explanation or a best theory out of many explanations that the evidence supports? Well, a common sense answer is not substantial confirmation. An obvious answer, or a wanted subjective answer to questions answered by multiple equal competing standing hypotheses, is not adequate. Inductive validity or formal logic alone is not a formal property of arguments. You can see I did a lecture in my philosophy section on logic, which is basically basically reason and argumentation, both formal and informal. So both arguments can have the same form, and both arguments can be or are supported by the same evidence. But how can evidence confirm my hypothesis? Is a confirmed hypothesis possible? Goodman says that a confirmed hypothesis is possible. Again, even if inductive validity is not a formal property of arguments, inductive validity is not a substantive property of arguments either. A strong appeal to common sense or practical wisdom is powerful, but is not allowed when looking for a logic of scientific discovery. Nelson Goodman suggests that there is a way to determine strength of inductive arguments, i.e., strength of a deductive argument depends on what language is used to state the argument. What does he mean by this exactly? Well, is reason relative to the language by which ideas are expressed rather than universal relativity? If so, can there be an art to scientific language? Many believe that an objective reason is expressed through an imperfect language, and so Goodman suggests that the limits of reason are bound by the limits of our language. This idea of a perfect or a precise language in science is not abstract. In fact, Goodman's proposal has application to actual science. So, how does one potentially evade the problem of induction other than by discovering new ways of relating evidence once established to theory? One way that has been suggested is the hypothetical deductive method, also known as HD method, an alternative to the positivist methodology. A scientific hypothesis is confirmed when its logical consequences turn out to be true. There are many advantages to this theory. However, there are fatal problems with this method. It looks appealing, but many logicians point out its conclusions do not always confirm what is actual legitimate science, i.e., any theory could be represented, for example, as a triangle, and then any statement could be represented as an L, okay, the letter L. So either you have triangle or an L is a logical consequence of the triangle. For example, heliocentrism, and I am 172.7 centimeters tall. So the conclusion is I am in fact 172.7 centimeters tall, but I cannot confirm the nature of the solar system by the observance of my height. This example is a funny example, but it illustrates why the hypothetical deductive method has problems. Logicians may want to use this method, but most scientists do not. What is the root of the hypothetical deduction problem? Every or any statement can or does confirm another statement. And as we know, that is false. You can have theory triangle, okay, which states that the cup is on the table, or the cup is on the porch that I just put down there. And then statement L could be aliens exist. The conclusion is that observing that the cup is on the porch does not prove or confirm the conjunction that the cup is on the porch and aliens exist. So sometimes the hypothetical deductive method works. For example, the triangle could be water boils at a certain temperature, which we know that it does by observing it or by repeated experience. The L could represent water raised to a certain temperature boils, and then observing water boils at a certain temperature, or water raised to a certain temperature boils, is a logical consequence of water boiling at a certain temperature. So the nature of the hypothetical deductive paradox. We also have Karl Popper, who talks about the raven's paradox. The hypothesis is that all ravens are black, or all A's are B's, for example. Observing black ravens or all A's proves that all ravens are black. So this logic of confirmation leads to the assumption that observing black ravens confirms that all ravens are black. Adding other evidence or holistic evidence helps. So do we have to take into account all human knowledge? There's some possible knowledge that could be hiddenly, possibly. But until we find that out, we simply do not know. Whether or not evidence counts as confirmation of a hypothesis will depend largely upon the context in which the discovery is made. A solution that Hempel provided to solve his own paradox is how does scientific discovery happen? He tries to answer this question by saying confirmation or refutation of theories should be based on the context of the discovery and the logic of the discovery. The observation counts as a genuine test, but most observations are not genuine tests. What is the defined nature of a genuine scientific test? You might ask, we have this thing called the curve fitting problem, or for any graphical data, there is an infinite amount of mutually exclusive equations that could fit the data collected. For example, you could have some data that you collect, and then you could have put it on a graph, and you could represent it by one graph, but you can also probably represent it on another graph, and then you could represent it on another graph, and then you could represent it on another graph. But you could represent certain data by using different equations or different graphs. For example, using the data and logic alone. By using the data and the logic alone, can we tell which graph projection is the best to predict future results, if they're all equally valid? So Goodman says no, they are all good representations of the same data. Is the simpler solution or the explanation the best solution? In Occam's razor solution, we have William Occam, writer of the medieval ages, philosopher of the medieval ages. The same data is presented in different ways. The simplest solution or presentation is not objective, since the data is perceived visually by a subjective person's experience, or what is simplest to one person may not necessarily be the simplest to another person. So the solution of the problem of induction, the appeal to natural kinds, a category of things that exist as part of the hidden structure of nature. We have metaphysical entities such as atoms, protons, neutrons, cells, molecules, etc. David Hume again rejected the solution of natural kinds. He saw that and admitted to physical objects, but he did not believe that metaphysical abstractions were a part of the real world of reality. But yet again, Hume was so skeptical indeed that he denied knowing anything unless he could physically see it, and this was because of his hard empiricism. So David Hume wondered what would even constitute as a natural kind. For example, what would constitute as an unnatural kind? Then we have Karl Popper. Karl Popper was extremely influential in the philosophy of science, and he was a philosopher as well. He wrote a book, a really good book. I recommend reading it, called The Logic of Scientific Discovery. He also wrote a book called Conjectures and Refutations, and he wrote a couple other books as well. I can't think of them right now off the top of my head, but I have several of them on my bookshelf, and I've read quite a few of them, and they're very, very well written. Karl Popper's principal concern was the problem of what he calls demarcation. So what are the distinguishing differences between science and pseudoscience or non-science? Karl Popper spoke directly in giving a reply to Hume's problem of induction before distinguishing between what qualifies as science and what qualifies as non-science or pseudoscience. Karl Popper, as well as David Hume, believed that induction does not work well in getting at the truth, not certainty. According to Popper, science is not based on induction, but deduction. According to Hume, the problem of induction meant that science had no rational foundation. Recall, the problem of induction is that a necessary connection between seemingly related things in nature, i.e. laws of science, laws of gravity, etc., but in reality, we never see the connection, i.e. we cannot see gravity. Therefore, if science cannot claim that there are laws in nature based on the fact that the laws of nature themselves cannot actually be seen or observed, and if all knowledge, scientific knowledge, or true knowledge, is based on perception, as many empiricists suggest, the laws of nature cannot be known to exist. All of the analyzed results of the past can be studied, but the patterns of and within the past can be taken for granted. Popper asks then, what makes two events the same, in the sense that the event is replicated or repeated? In order to know that two events are the same, the data must be interpreted. And I guess you could say, when Popper asked what makes two events the same, this reminds me of Heraclitus, who talked about the river, and how he says the river is never the same because it's always flowing and it's always changing. So it's never the same river, but in a sense it is. Popper talks about the fact that in order to know the two events are the same, the data must be interpreted. And in order to interpret the data, a frame of reference is needed, which he calls the theory latedness of observation. Is that every observation is made with a certain background set of expectations, theoretical context, or frame of reference. So events are never only similar or only different, but are similar or different in certain regards or respects, or a difference of degree. So we have these respects demand a framework, a theoretical framework, Popper suggests. Since Hume thought that knowledge is based on induction, he knew that he could not have any knowable knowledge or justified true belief. Popper suggests to a dead Hume that knowledge is not based at all on induction. Popper suggests that repetition is seen in nature because we have learned to expect repetition. In other words, we see patterns in nature because we naturally find it and we seek it out. In a sense, humans impose regularities on the world and learn about imposed regularities through trial and error, conjectures and refutations. Popper emphasizes the hypothesis first, or the expectation first. Test the expectation by many observations. Observations are guided by a direction of what to observe, or what information that is relevant to observe. Popper does not believe in innate ideas, an idea of Plato, Descartes, etc., but that humans are born with expectations, i.e., baby infant expects its needs of hunger to be met or satisfied. These instincts are not innate ideas, but these instincts fuel the hypothesis of ideas and predictions. Popper also, in a way, alludes to the fact that experiences in regards to the ideas of Immanuel Kant. We have Popper, who says that the propensity to look for regularities brings forth dogmatic thinking. It is one committed to an idea and refuses to recant said idea. He's talking about dogmatism, the critical attitude, and what's called the Oedipus effect. Hume's critical idea, or critical attitude of scrutiny, is the ability to openly and willingly criticize any idea with an open mind. Popper seeks to agree with Hume here. But in light of David Hume and Karl Popper, we should not think that any idea should go unchallenged. Matter of fact, dogmatic thinking can convince one to look for confirmation of their theories. The Oedipus effect, for example, could be seen as Columbus's voyage to India, okay, which was actually the New World. A scientific attitude of a historian, philosopher, scientist, etc., should welcome opportunities to falsify their theories with critical scrutiny and in honesty, and this goes for theology as well. So, in order to be genuinely scientific, we should welcome opportunities to falsify our theories with critical scrutiny. All theories should be seen as falsifiable until proven otherwise. Popper asks what qualifies a theory as a scientific theory. A good specific prediction based upon an expectation and experience. We can combine actual science, which is Einstein's relativity theory, versus pseudoscience, like Karl Marx's historical materialism and Sigmund Freud's psychoanalysis. Those two are both ideologies and it's not really science, but pseudoscience. So Popper urges us to reject ideologies and illusions of dogmatism that are not based on evidence and label them as pseudoscience until proven otherwise. Then we must ask what is scientific. So we might think of things like neo-Darwinism. We might think of things like intelligent design, which are neither scientific. Are neither scientific? Both are scientific, or is only one scientific? Anyways, we need to think hard on these questions. Conclusions on Popper is first that confirmations for any theory are everywhere if searched for. Confirmations should only count if they result from risky predictions. Every scientific theory prohibits some things from happening. A theory that is not falsifiable is not scientific. Every genuine test of a theory is an attempt to falsify it. We should have a tight and small margin of error. And unfalsifiable theories are not necessarily false, but they are not scientific. Inductive inference is a myth. Science operates by conjecture and refutation. This is big for Popper. Experiments are tests in the attempt to refute the hypothesis. Many scientists still believe in induction because they might mistakenly think it is an answer to the problem of demarcation. Induction is an insufficient demarcation. Invoking probabilities will not save induction, and science uses deduction by way of conjecture and refutation. Popper makes a bold claim. In a sense, he thinks he knows scientists better than they know themselves. He claims that scientists are not actually using induction, even if they think that they are. Can induction be a science? According to many practicing scientists, it can be. According to Karl Popper, a philosopher of science, he says no. But why is Popper so radical? After all, many scientists think that induction is essential to the scientific work. It is, matter of fact, the combination of induction and deduction that have created the scientific method itself. So, how do we solve Hume's problem of induction? According to Popper, by deductive method. Does belief mean a tentative acceptance of an idea combined with fallibilism, or a willingness to admit that one may be wrong, and a willingness to revise your previous thought idea if necessary? So, Karl Popper and solving the inductive problem. We never inductively infer a theory from the evidence. Rather, we hypothesize a theory and then we attempt to falsify it. We can never certainly prove a theory true. Rather, we only fail to falsify it after many unsuccessful attempts. Since falsification is a deductive matter, although itself is an inductive principle, the problem, according to Popper, of induction never arises. Then we have objections to Popper's falsification theory. We're going to finish with Popper, and then we're going to go to Thomas Kuhn and normal science. Okay. Objections to Popper's falsification theory. Falsifiability is at best a necessary but not sufficient condition for a theory being scientific. What are other necessary conditions in order for an idea to be scientific? We have a term called holism, which is about testing means that that abnormalities are not counterexamples, as is pointed out later by Thomas Kuhn. There needs to be room for margins of error in testing. Popper gives almost zero answers in discussing what distinguishes abnormalities from counterexamples. Or no, not abnormalities, but abnormalities from counterexamples. For example, one objection would be probabilistic science. But scientific systems cannot be studied scientifically. This can be seen in quantum mechanics. For example, population genetics, social science, economies, social psychology, etc. So, the confidence problem. The most tested theory is the more likely to be the true theory. More likely, of course, is inductive thinking. And, of course, as a historian, we have to use inductive thinking. We use evidence, but we have to use inductive thinking because we say what's more likely the case, what's the highest probability, what out of this happening or that happening, which one has the more likely chance of being correct. Examples of objection from the history of science. We see that the sun is larger than the earth, and that the heart circulates blood. These claims no longer scientific or pseudoscientific because they have been tested enough in order to be marked as unfalsifiable. For example, we know that the sun is larger than the earth. We have tested it and we have observed it over and over and over again. We know that the heart circulates blood. This has been observed over and over and over again. These discoveries are not falsifiable, and Popper has a problem here. He makes these kinds of claims axiomatic concepts that we saw in the works of like Ayn Rand, things like identity and things like existence. What if we cannot prove all things to be actual 100% falsifiable or unfalsifiable? What was Popper right about? Well, Popper was right about that any data is immune to new data. Any data that is immune to new data is not scientific. He is also right in saying that scientific theories must make predictions that have the potential to be false. And he also says that many theories appear to respond based upon new data, but actually do not. But what was Popper wrong about? He was wrong about saying few ideas in science are straightforwardly falsifiable. Not all statements and theories can be neatly divided into the science or non-science categories. And also, some theories can be more or less scientific than other theories based upon new evidence findings. Thank you for watching this lecture. I got it under 30 minutes, which is my goal. It is my goal to get all of these science lectures within this playlist under the 30-minute mark. In the next video, we're going to talk about Thomas Kuhn and normal science. So we're going to talk about, in the history of science, we're going to talk about the philosophers of science, Thomas Kuhn. And so this lecture is going to be titled, I don't know if I want to title it Empiricist, Positivism, or Logical Empiricism, my bad. Since I titled the last one Logical Positivism, I might title this Logical Empiricism, but I'm probably just going to probably put this under Karl Popper, since the majority of this lecture was on Karl Popper. I'm probably just going to put this title this lecture Karl Popper. So anyways, thank you for watching this video. I hope it was informative. I hope you were able to learn something about science, about the intricacies of the hypothetical deductive method, the problem of Hume's problem of induction, and why Karl Popper thinks that deduction and the deductive method is the only way of truly understanding whether something is or whether something is not. Thank you, and I'll see you in the next one.